Pluto is a remote and bewildering, more unpretentious planet that was once a piece of our sun-stimulated system's planetary get-together. However, later astounding announcements by perceptible astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an astonishing disclosure. They suggested that this cool world is on a potential impact course with Neptune. But how could it be that this could wind up as a matter of fact? What might be the repercussions of such a giant event? Are we seeing an intriguing colossal unconventionality? Or is there something else to this oncoming vast fight? Join us as we analyze the potential outcomes of a Pluto-Neptune impact. Pluto, a previous planet that was renamed as a dwarf planet, is considered this way partially due to its stunning orbit, which remains a subject of interest and assessment in the cosmic community. As indicated by ongoing figures by leading specialists, Pluto's orbit is dangerously close to Neptune's, with both Neil deGrasse Tyson and Michio Kaku sounding the alarm about a possible dangerous collision between these two planets that could represent a serious danger to Earth. How is such an event even possible? Pluto's circle around the Sun is unlike any other planet in our close planetary system. It requires a shocking 248 years to finish a single orbit. Since its discovery in 1930, it hasn't most likely finished one full revolution. However, it doesn't stop there. Pluto's orbit is marked by its particularly bended shape, meandering unbelievably distant from the almost round orbits of the significant planets. What makes Pluto's orbit significantly more shocking is its inclination, still hanging out there at 17 degrees to the ecliptic plane. How Pluto follows is much more slanted compared to other planets. This tendency and elongated nature add layers of intricacy to its orbital arrangement. One of the most interesting parts of Pluto's orbit is its union point with Neptune's orbit. For around 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, testing what we could anticipate from their positions in the planetary system. This prompts the natural inquiry: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of different planets. The evaluation of Pluto's orbit began not long after its discovery. Initially, cosmologists attempted to understand its peculiar way as compared to planets whose orbits lie relatively close to the ecliptic plane. Pluto's orbit stood apart with its steep inclination and stretched shape. The mystery grew with the affirmation that Pluto's orbit indeed crosses Neptune's. The security of Pluto's orbit amidst these complexities is proof of the intricate design of space mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and impact each other with their gravity. It's like attempting to predict where they will go based on where they start and how they pull on each other. For Pluto's case, this issue shows how the orbits of Neptune and the Sun's gravity all interact in a complicated way. The terms libration and resonance, alongside the Kármán waving, are fundamental for this conundrum, as displayed by astrophysicists. What keeps all planets in their orbits is libration. In the specific context of Pluto and Neptune, this term suggests that whenever Pluto crosses Neptune's orbit, it's situated no less than 90 degrees away from Neptune. This spatial separation is vital in keeping their orbits from impacting. Resonance, on the other hand, refers to the periodic movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or some other giant planet, it's arranged entirely over their orbital plane, providing an extra layer of security from potential impacts. Another critical component of this situation is the Kármán waving, named after three scientists, von Zeppelin, Kapuz, and Lev, who studied how objects move in space. It describes how three celestial objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This pull influences how they move. In Pluto's case, the Kármán waving helps us understand why its orbit around the Sun is so unusual. Regardless of its seemingly inconsistent path, Pluto's orbit remains stable for seemingly billions of years. This suggests that Pluto's journey around the Sun has a certain order to it, even though it seems erratic at first. Predicting enormous events, particularly when they involve chaotic orbits like Pluto's, presents significant challenges. The inherent volatility of these systems means that long-term predictions are often laden with uncertainties. While mathematical simulations provide a strong method for understanding and forecasting the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models heavily depend on the accuracy of initial conditions and the complexity of the interactions they simulate. Any minor error or deviation can lead to vastly different outcomes, making accurate predictions a daunting task. Moreover, the turbulent nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made great strides in understanding space, the case of Pluto serves as a reminder that our knowledge of the universe still remains limited. Understanding the gravitational impacts of the giant planets on Pluto's orbit provides significant insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have substantial effects on the stability and behavior of other bodies within the system. So why are prominent astrophysicists recently raising concerns about a potential collision between Pluto and Neptune? Despite these eccentric forces trying to keep such an event from happening, Neil deGrasse Tyson, a prominent astrophysicist and key advocate for advancing cosmology, offers an intriguing perspective on the mysteries of our nearby planetary system, particularly the stunning case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, provides immediate commentary on the evolving nature of celestial mechanics and the public's interest in the strange domains of space. Tyson's stance on Pluto's renaming is grounded in the ever-evolving knowledge of our local planetary system. He sees the renaming not as a downgrade but rather as a significant change in alignment with our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of constant learning and change. He sees the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The interest in these questions, especially the potential connections between Pluto and Neptune, highlights the dynamic and unpredictable nature of our nearby planetary system. His work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another respected physicist and futurist, offers an alternative yet complementary perspective on the mysteries of space, focusing on the often turbulent forces that shape our universe. Kaku is known for his ability to connect complex scientific ideas with visionary concepts, making him a crucial voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's perspectives on Pluto and its orbit underscore the need for continuous observation and advanced modeling to predict and understand potential cosmic events. He sees the connections between celestial bodies as a critical area of study, not just for academic interest but also for practical applications. The potential impact between Pluto and Neptune, for example, isn't just a hypothetical situation but a reflection of the dynamic and often violent nature of space. Kaku's futurist viewpoint urges us to consider the broader consequences of such events, from their impact on our understanding of the solar system to the possible need for future space interventions. His perspective highlights the importance of being prepared for the unexpected in space. Kaku suggests that the more we grasp the forces at play, the better prepared we will be to navigate and potentially mitigate the effects of significant events. Both Tyson and Kaku's viewpoints converge on the idea that space is an area of boundless discovery and that our current understanding, while significant, is still limited. Their emphasis on the need for ongoing research and advanced modeling mirrors the growing nature of space science. They highlight the importance of not only understanding celestial mechanics as they are now but also speculating on how they might change in the future. The potential impact scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It emphasizes the need for robust scientific inquiry, cutting-edge technology, and a willingness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a revitalizing call for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is widespread scientific agreement that long into the future, the orbits of Pluto and Neptune will remain stable due to their mean motion resonance and the various gravitational forces acting on them. Therefore, a direct collision between Pluto and Neptune is incredibly unlikely. However, the intricacies and potential disruptions in orbital dynamics still suggest that space experts should continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they might present. While the possibility of a Pluto-Neptune impact is mostly theoretical and considered improbable with current understanding, it underscores the importance of continuous review and observation in space science. Advances in technology, including more sophisticated telescopes and computational models, will assist astronomers in refining their simulations and predictions, ensuring that we stay ahead of the dynamic and ever-changing nature of our nearby planetary system. Tyson's perspective on Pluto's renaming, alongside Kaku's emphasis on the unpredictable nature of celestial mechanics, both highlight the need for continuous investigation and a flexible understanding of our universe. The potential impact scenario, while emphasizing the dynamic and complex interactions within our nearby planetary system, ultimately reminds us of the vast yet still murky spaces in our understanding of space. Through continued investigation and observation, we strive to unravel these mysteries, ensuring that our knowledge stays in step with the ever-developing universe. Pluto continues to dazzle researchers and space enthusiasts alike with its remote, baffling nature. While its status as a dwarf planet has long been debated, its orbit and intriguing characteristics continue to captivate scientists. Recent developments have once again placed Pluto in the spotlight, with the potential for a gravitational interaction between Pluto and Neptune becoming the focal point of attention in the space community. With Tyson and Kaku bringing this topic to the forefront, the discussion surrounding a potential Pluto-Neptune impact is sure to spark further interest and research. The investigation of these enigmatic celestial bodies holds the promise of uncovering new insights into the mechanics of our planetary system. As we peer deeper into space, the dynamic and unpredictable nature of our celestial neighborhood only underscores the need for caution and ongoing investigation. While the potential interaction between Pluto and Neptune remains a topic of scientific interest, it is crucial to consider the broader context of space exploration and the methods used to study celestial bodies like Pluto. The discovery of potential risks, such as a possible Pluto-Neptune impact, serves as a stark reminder of the immense complexity and unpredictability inherent in the universe. It highlights the complicated mechanics at play within our local planetary system, where even the most seemingly stable orbits may harbor hidden vulnerabilities. This thought draws attention to the sophisticated tools and methods used by space experts and physicists to understand the movement of celestial bodies. One important tool used in such studies is mathematical simulations, which allow scientists to predict and model the behavior of planets and dwarf planets over extended periods. By inputting known parameters like mass, speed, and distance of celestial objects, these simulations can project potential future movements and assess the stability of orbits like Pluto's. Such models often rely on powerful computers and advanced algorithms to handle the vast amounts of data and complex calculations required. This method is especially important when studying objects with irregular orbits like Pluto, whose path around the Sun is so distinct from the other planets in the solar system. Additionally, the role of gravitational interactions between celestial bodies cannot be overstated. As mentioned, Pluto's orbit crosses Neptune's, and the gravitational pull between these two bodies could hypothetically lead to unusual outcomes over very long time scales. However, due to the resonance between Pluto and Neptune, their orbits remain locked in a stable relationship. As researchers continue to study the dynamics of Pluto's orbit, they have uncovered fascinating new insights into how gravitational interactions shape the paths of celestial bodies. The fact that Pluto's orbit crosses that of Neptune yet remains stable is a testament to the complexity of orbital mechanics in the solar system. This stability, despite the apparent risk of a collision, raises important questions about the long-term behavior of celestial objects. Scientists have long speculated that such interactions might be more common than previously thought, especially in the outer reaches of the solar system, where many other dwarf planets and small bodies follow similarly irregular orbits. One of the intriguing aspects of this ongoing research is the role of other celestial bodies in influencing Pluto's orbit. While the Sun's gravity is the primary force governing the movements of objects in our solar system, the gravitational pull of the larger planets, particularly Jupiter and Saturn, also plays a significant role in shaping the orbits of smaller bodies like Pluto. The positioning and movement of these massive planets can, over millions of years, exert a stabilizing effect on smaller bodies, helping to prevent potential collisions or drastic orbital shifts. This is especially true for Pluto, where the combined gravitational effects of Neptune and other gas giants may have helped to maintain its relatively stable orbit despite its eccentric path. Moreover, the study of Pluto's orbit and its relationship with Neptune provides valuable information about the early history of our solar system. The current configuration of these two distant bodies could offer clues about how the solar system formed and how the planets and other objects interacted during its formation. Some scientists believe that the unusual orbits of bodies like Pluto may be remnants of the early chaotic stages of solar system evolution, when planetary migration and gravitational interactions were far more tumultuous than they are today. This ongoing exploration of Pluto's orbit not only deepens our understanding of our own solar system, but also offers a glimpse into the broader dynamics of other planetary systems. As technology advances, astronomers are increasingly able to observe distant exoplanets and their moons with greater detail, leading to discoveries that may mirror the complex interactions observed in our own system. The study of Pluto's orbital mechanics is just one piece of a much larger puzzle, and the insights gained may ultimately help scientists understand the forces that govern the evolution of planets, stars, and galaxies across the universe.